A fifth way of saying something about what is between the treatment and the outcome is to actually identify a specific mediator. In which case, we are actually able to say how much of the effect of the treatment on the outcome can be attributed to this specific mediator. Now, that's something we all want, right? A necessary precondition, obviously, is that we actually have data on this specific mediator. Now, let's for now assume that we have a non-random selection in not only the treatment, but also in the mediator, and that everything is linear. How does this then work, mediation analysis? Well, first there's the direct effect of the treatment on the outcome, which is the change we would see in Y under a unit increase in T. So we actually administer the treatment, but we keep this specific mediator constant. And so that can be seen as sort of the residual effect of T on Y. So within the example of the effect of airbags on lethal accidents, it is actually the change in the chance of getting into a lethal accident thanks to having an airbag while keeping this specific mediator that we are interested in constant. So we keep speeding constant and then see what the effect is of airbags on lethal accidents. Yeah, so in the equation form, as it says at the bottom here, is basically the relationship between Y and T while adjusting for M. So while keeping M constant. Alright, so then secondly, the indirect effect. And that's a little more involved, but let me explain this step by step. I first provide the definition of the indirect effect and then explain this in more detail. It's the increase in the outcome given that we hold the treatment constant, but set the mediator at the level that it would have taken if we had increased T by 1, i.e. we look at the relationship between T and Y, and then look at how M would have affected Y if M changes to the extent that T affects M, but we actually hold T constant. Now that sounds a little convoluted, right? Basically, look, the way to look at it is as follows. We are interested in the unbiased effect of the mediator M on the outcome. Right, so that's our main focus. That is basically gamma 1. Right, so how does speeding affect the chance of getting in a lethal accident? But we actually have to multiply that by how much airbags affect speeding, right? That's the beta 1. So the indirect effect is beta 1 times gamma 1. So in terms of the airbag, the chance on a lethal accident, given that we hold having an airbag constant, but set speeding at the level that it would have taken if we had introduced an airbag. So in equation form, there's two equations here. So there's the equation that we saw in the previous slide. So that's the relationship between Y, M, and T. And now we are not interested in gamma 2, but in gamma 1. And then there's the first part, that's simply the relationship between T and M. So here we go, and that's beta 1. Now, it may sound weird to estimate this relationship between m and y, and then hold t constant. So we're interested in the effect of a mediator on the outcome, but we keep the treatment constant, right? But that is exactly what you want, because t here is actually a confounder. We are interested in the unbiased effect of m on y, but as I've shown here in this causal diagram, t functions here as a confounder, because t is a common cause of the mediator, but also and the outcome. So we have to adjust for t in this relationship, right? So we have to keep t constant, but set m at the level that it would have taken if we had administered the treatment, right? So within the example of airbags, that is exactly what you want, because you are interested in how speed affects lethal accidents, and you don't want airbags here to confound this relationship, to cause some bias, because airbags are not randomly distributed between the control group, the non-speeders, and the treatment group, right? So that's how it works. So that's how we get this relationship between m and y, i.e. the coefficient gamma 1. So this all sounds pretty straightforward, right? Once you also get this the second step of how to derive the indirect effect. Unfortunately, in practice, it's a little more complicated, because the assumption of random assignment into the mediator is unlikely to be met. People may choose some mediator, for example, in this case speeding, for reasons that are also related to the outcome. So the relationship between m and y is likely to be biased even when we adjust for t, because there are maybe these confounders here, the cm. For instance, within this context, being a frequent user of back roads rather than the usual freeway routes may affect both your speeding levels and also the chance of getting a lethal accident, because it may this is a certain type of driver, right? And those drivers may be more likely to get into a lethal accident. So as a result, if we would not take this confounder into account, the relationship between speeding and lethal accidents is confounded. Normally we don't need to worry about this confounder, but now we are actually adjusting for m, right? M is a collider, but as we learned, if we adjust for m, we open this path here. Airbags and those confounders become related actually when adjusting for speeding. And then we're in trouble, right? Because we open this non-causal path. Now you would say, well, we just adjust for Cm then, for any confounders. Yeah, sure. But the trouble is that we may only know some of the possible confounders, and you also need data for all of those confounders, right? So that's not a very credible strategy. Because that is simply the strategy of selection on observables. Right? So the first design that we discussed in Econometrics 1, and that only works under very strict assumptions. Basically, if we exactly know all possible confounders, and we also have data for all of those confounders. All right, so what are we going to do? Now, it would be ideal if we can randomly vary m, because then we can actually easily identify the unbiased effect of m on y. Simply, very similar to estimating the effect of t on y. We just instrument t, and then we get the unbiased effect on y. Now we are going to instrument m to estimate the unbiased effect on y. Now, in practice, this is not so simple because finding a good instrument is not easy. And now we do not only need an instrument for the treatment, CT, but we also need an instrument for this mediator, speeding, right? And those two instruments should also not be related to each other. i.e., in practice, this is not too likely to work. Finding two such instruments is, in most contexts, too difficult a task. So, and that's not the only thing, because there's more assumptions, like we actually make the assumption of linearity, and there may be interaction effects. There may be multiple mediators interacting with each other, in which case things are much more complicated. i.e., to summarize, what most economists say is that forget about it. It's not going to work. Directly identifying a mediator so that we are able to say how much of the treatment effect can be attributed to this specific mediator is too challenging. So what we generally see in economics papers is that authors tend to focus on the relationship between T and M, which is easy, because that is, as long as we have as good as random variation in T, and you have data on this mediator M, then you can always identify this relationship, right? But economists tend to stay away from this second step here, M on Y, and this second step is obviously necessary to identify the indirect effect. So if we can't, then we only say, well, we see that T affects this supposed mediator, but we don't know the second step, how much the change in the mediator affected the outcome. And so we cannot really say how much of the treatment effect can be explained by this specific mediator. Now, there's a new approach actually that was introduced last year in a paper, well, it's actually 2020, in a paper by Christian Dippel et al. This is really new, so it has not been applied much yet. They have their own paper actually, in which they apply this methodology, which has just been published in the Economic Journal. There's an earlier paper by Sula Alam and Seda Ertak, but that's about it, right? So this is brand new, but I think it's worth going over their method, because it may well be that we're going to see more of this in the very near future. And more generally speaking, there's a lot of interest among economists now, in applied micro at least, in mediation analysis. Now, the unique thing about this new approach is that we don't need a second instrument. So we can keep working with this one instrument for T. As long as you have that instrument, then you can actually use the methods, as long as you meet a set of assumptions that I will discuss. And the idea is that when we use this instrument also for the mediator, then that actually means that we use this confounder here and any confounder of the relationship between the treatment and the mediator as our sort of implicit instrument. Let me explain this in more detail. So, if we would be able to observe a confounder of this relationship, then we could actually directly use it as an instrument. Right? So, but we don't. And that is the trouble here, is that CT is actually unobserved. But the basic idea here is that by using this instrument CT as an instrument for M, while adjusting for T, we actually implicitly use CT as our instrument. And then obviously, as in the case of any instrument, CT should not affect the outcome directly. It should only affect the outcome by way of the mediator, right? So that's the usual exclusion restriction of any instrument. All right, so let me explain this in the following way, and I drew the causal diagram a little different, so that it should be clear what is a confounder and how adjusting for G affects a confounder. Now, we are interested in the relationship between the mediator and the outcome, and we want this relationship to be unbiased, right? So, as we discussed earlier, we have to adjust for T here because T acts as a confounder. T affects both M, but it may also directly affect Y. This is the direct effect, right? So basically, if we are interested in the relationship between M and Y, we have to adjust for T. Now, but if we instrument M with ZT, then we open a very interesting path, namely this red path. So that, this is the confounder of relationship between M and T, right? As I showed earlier, and that path was closed because T acts as a collider here, right? So as long as we leave T alone, then this path is closed. Now, as we discussed earlier, as soon as you start adjusting for T, then you open a path that has a collider. So, but that's exactly what you want. So CT and CT now become directly related because we adjust for T. But that's exactly what we want, because then we open this path CT, T, CT, and Y, i.e. CT acts as a way of triggering this implicit instrumental variable CT, and as a result we get as good as random variation in M, which is wonderful obviously, because then we can actually identify the effect of M on Y. Right, so that is the way it all works, and obviously again the exclusion restriction, usual exclusion restriction, needs to hold, namely that this implicit instrument that we're using here, which gets sort of triggered by way of the instrumental variable CT, this should not have a direct effect on the outcome. And so basically saying that this sphere here should be independent from this sphere. So any confounders of this relationship should not have direct effects on the outcome. So, and then following the method, so we not only need the relationship between M and Y, but also between T and M, but that's very straightforward. There's nothing special about this relationship. We discussed that before. As long as we have as good as random variation in T, we can easily identify the effect of T on M rather than the usual T and Y relationship, right? So because any confounders here are of no worry, because we have as good as random variation in T. So it all comes down to estimating three equations. First of all, there's the total effect, the relationship between the outcome and the treatment. and you know, we are already familiar with that because that's identifying the average Zeeman effect. Then there is the first part of the indirect effect, namely the effect of the treatment on the mediator. That's also straightforward, so that's not the effect of the treatment on the outcome, but the treatment on the mediator. So we just replace y by m, and that's all. And then there's actually the more complicated second part of the indirect effect and also the direct effect, and that is the relationship between the outcome, the mediator, and the treatment, and then we instrument m also with this instrument ZT. One example of this method is provided by a paper that has just been published by the same authors in the Economic Journal, where they look at the effect of economic shocks, so in this case shocks to imports, and how that affected voting for an extreme right party in Germany, Alternative für Deutschland actually, and then they are actually able to attribute part of the total effect of import shocks on voting for extreme right parties to a specific mediator, namely labor market adjustments, and it all works by way of unemployment. So basically import shocks lead to unemployment, that's the reasoning, and therefore it affects voting for extreme right parties, and any confounders here of this relationship, which are then used as our implicit instrument, should not directly affect voting for extreme right parties. Now, that's they actually say this also in so many words in their paper. They say the following: we have no reason to believe that there is an unobserved variable orthogonal to local labor market adjustments that significantly affects the relationship between import exposure, i.e. T, and voting behavior, Y. But this is also all they say. So they don't really explain in terms that everybody can understand why this should be true. Basically, they say, you know, this is so trivial that we don't need to explain this any further. Another example is provided in a related paper on a stata command that you can use for their method, and then they look at the effect of Protestantism on economic prosperity, and they're interested in how much of the effect of Protestantism on economic prosperity can be explained by the share of the literate population. And they actually have an instrument for Protestantism, namely distance to Wittenberg. Basically, that's where this guy here, Martin Luther, came from. And they can actually use this instrument to both look at the average Zeeman effect of Protestantism on economic prosperity, but they can also use this as an instrument for M, the share of the literate population. This is one example, one other example of the use of their method. And again, the implicit assumption here is that any confounders here do not have a direct relationship with economic prosperity. So those are two very distinct spheres. And then finally, we can actually also use their method in a randomized controlled trial, but then we need an instrument, so i.e. we need some kind of encouragement design, encouragement of the treatment. For instance, we cannot force students to go to the gym, but we can encourage them to go to the gym by providing free gym cards. So in that case, provision of free gym cards is our source of as good as random variation in going to the gym or no, and as a result, we can actually identify the effect of going to the gym on some outcome, for example, academic performance. But very importantly here, as soon as we do that, we do need to start worrying about any confounders here. We usually do not have to worry about it. It's sort of the non-random part of the variation in the treatment. As soon as we start using CT as our implicit instrument, by instrumenting M with ZT, we get this non-random variation back, and we need to worry about any direct effect of this confounder on the outcome.